Hello and welcome to our new screencast, which is about sensor scaling and PDM, respectively PWM output. My name is Ralph Emberger and I will guide you through that screencast. You will learn in this screencast how to scale a sensor on the basis of the linearization firmware and also how to output it via PDM or PWM. I have the PCAP02 Plus software already open and will select here the pressure linearization firmware from the pre-configurations available on the first tab page. It reminds me of downloading some E2PROM parameters, which I do by clicking right here, wait for the red light to turn off and read back again to make sure the download was successful. After that, by clicking Init Reset, Write Config and Start Measurement, I can start a measurement and see if the connection is working and the measurement runs. I now show you the hardware I have connected to my PC, which is a PCAP02 standard evaluation kit with some fixed ceramic capacitors connected in floating mode from PC0 to PC3, so I can vary them. And I have an oscilloscope probe connected here on PG2 output. So now I'm starting again the measurement by clicking Init Reset, Write Config and Start Measurement, and have a look at the results we get down here in the CI ratio and the other parameters here. What I recognize is that not the right capacitive ports of the PCAP02 are selected, so I need to select from 0 to 3 here to reflect the two floating capacities I have connected. So now if I change a capacitor on the second port, I don't see, however, any change here in the value, and that means that selection of the capacitors is not done right. So I need to change that to tell the firmware which pair, and in my case it's the first pair of capacitors I want to compare, I want to select. So that's done by cselect 0 setting to 1 and the rest to 0. Now if I change the capacitor, I also see some change in the CI ratio, and that is what I would expect here. An overview how to select the capacitors right here with the parameters to tell the firmware which one you want to select you can find in the linearized datasheet, by the way. So let's have a closer look now at the capacitors I'm using here. So the reference capacitor is 10 picofarad, meanwhile the varying capacitor, the sense capacitor, is in the range between 4.7 pico and 22 picofarads. So I basically have a range from half to the double of the reference capacitor, which will be reflected in the ratio later. I assume further that those capacitance change reflects a pressure sensor, and which ranges between 5 and 25 psi. This simple sensor scaling can be done by the linearization window and using 2 points which reflect the edges of the pressure ranges and the corresponding CI ratios. I will now show you how to do this. First you select Tools and Linearize to get the window dedicated to the linearization, and now you fill in the upper and lower range of the pressure range, that means 5 psi at room temperature 25 centigrades, and then you acquire the corresponding C ratio by pressing this button. Make sure here's C ratio selected, and do the same for the higher pressure. So here it's 25 psi. I'm varying the capacity here with my fixed capacitors. In reality, of course, you would need to apply pressure now to your sensor. Once this is done, you can import that data to the E2PROM parameter set by pressing the Refresh with Linearization Data button, and then write the parameters down to PCAP02 again. Now, after having the basic scaling done, I will show you how to configure for PWM or PDM output. So you can see here tapping at PG2 of the board gives us a high output all the time, and I will show you step by step how to configure that by the front panel software. So the easiest way is really to press here that load example settings button, which preloads some values and you can adapt them as needed. One very important point is here to select the output of to PG2, since the standard output for the PWM PDM output is PG0. Unfortunately, that pin is however occupied by the SPI lines. So if not I2C is used for interfacing, you need to free that output to PG2 to get an output at all. After that basic settings, I can now configure the PWM output to my requirements. I select, for example, 14 bits for the output and will now calculate the slope and offset parameters I want to fill in here. So 14 bits corresponds to 16,384 steps, and I divide that by 20 psi, which is the range I formally configured between 5 and 25 psi, if you remember. And this gives me my slope of 819, which I fill into this field. And now I basically also need to calculate the offset, which happens the same way. I have an offset of 5 psi, since this is my lower range limit, and 5 times or 5 psi times the configured slope of 819 gives me now my offset of 4,095 to fill in to this field. Now if I do that with a minus sign, you already see here on the output that it now goes to low because I'm in the lower range of the sensor. I now switch to the higher limit, and you see the output is already between 0 and 1, and if I go to a value in between of that, I get the expected output, which is here roughly like 70-30% duty cycle. Basically, we have the PWM output as desired already. Nevertheless, I want to show you an alternative of selecting a high frequency clock instead of a low frequency clock, to be selected here with HFX1 and to be activated by setting the clock to a permanent running clock as done here. This gives me a high frequency clock as a base for the output for PWM. The disadvantage is the higher current consumption. The advantage is that a simple low pass filter can be used for generating the analog voltage. I have here a simple first order low pass filter, as you can see here, and I connect the probe of a oscilloscope now to it to show you the analog voltage output. Now we have the corresponding analog voltage for the 70 to 30 duty cycle, and if I change the capacitance, since we get the high and the low voltage signals accordingly. Finally, I want to mention that you can select in this field here between PWM and PDM, and although in this screencast the output has been demonstrated on the basis of PWM, in most cases PDM is the recommended output option. Therefore, let's have a closer look at the two options again. With PWM you have a fixed frequency in which the duty cycle changes, as illustrated here in that graphic, of 25, 50 and 75% pulse duty ratio. Meanwhile, with PDM you have a bit stream that corresponds to the analog signal's amplitude, as illustrated in this simple sine wave example from Wikipedia. And thus the envelope curve of that PWM output varies with different pulse duty ratio and thus different frequencies. One major advantage of PDM over PWM is that it can be operated at lower frequencies and or lower order low pass filter. Another advantage is that it has a much lower ripple than PWM if same frequency and low pass filter is assumed. So if you are free to choose, we recommend the use of PDM. Of course, at the end of the day, your application's requirement determine the use of either PDM or PWM. Of course, PCAP supports them both. Okay, so with this we reach the end of the screencast. I hope you enjoyed it and found it helpful. For further screencasts also of our other product lines, please check out our website at www.acam.de and go to the download section. Thank you and goodbye.